I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is Lecture 4 of Module 8. Today I will discuss the importance of first law of thermodynamics and few examples. This is the last lecture of Module 8. Here I will mainly focus in this lecture that the outcome of first law. Next, the path dependency of work done and few examples in the first law of thermodynamics. Now, the outcome of first law. The importance of first law of thermodynamics. Now, there are three importance of first law of thermodynamics. First of all, I introduce about the first law of thermodynamics. First law of thermodynamics states that if the change of internal energy is du due to supplied of heat to the system, dq amount of heat to the system, and the work done by the system is dw, then from first law we know that du change of internal energy du equal to dq minus dw. That means that is dq equal to du plus dw, and in hydrostatic system this becomes dq equal to du plus pdv. I repeat again, if dq amount of heat is supplied to a system and during this heat supply, if the internal energy of the system, change of internal energy of the system is du, and during this process the amount of work done by the system is pdv, then dq equal to du plus pdv. That is, first of all, you know that this is the conservation of energy. That means first law gives the conservation of energy. And new thing is that the first law gives the concept of internal energy of system. That means here the importance is that first of all we know the existence of internal energy function. This is the first outcome. Therefore, I write here one by one the existence, the importance outcome are the importance outcome are the importance outcome are the importance outcome are arises in first law. Now, or from the first law of thermodynamics, from the first law of thermodynamics First one is the existence of internal energy function. The existence of internal energy function. Existence of internal energy function. Of internal energy function. Internal energy function. Internal energy function. In the similar way, from the zeroth law of thermodynamics, we get the existence or concept of temperature. At the same way, from the first law of thermodynamics, we get the existence of internal energy function. Next one, principle of conservation of energy. Principle of conservation of energy. Principle of conservation of energy. Conservation of energy. This is the second one, because dq amount of heat is supplied to the system, the change of internal energy of the system is du, and during this process the work done by the system is pdv. Therefore it gives the principle of conservation of energy. Third one is the definition of heat as energy in transit by virtue of a temperature difference. Third one is the definition of heat. The definition of heat as energy in transit of a temperature difference. These are the three main outcomes of first law of thermodynamics. Next one, the next point was the work done. Next point is work done. Next point is work done. Work in changing the volume of a hydrostatic system. Work done in changing the volume of a hydrostatic system. Hydrostatic system. Suppose a cylinder, here is a cylinder of, we apply a force F, and the piston, this piston due to applying a force, the piston is displaced by an amount dx as shown in this figure. This is the displacement. This is the displacement. This is dx. And we consider the cross-sectional area of the cylinder. Cross-sectional area of the cylinder is alpha, and pressure at the piston is P. Pressure at the piston equal to P. Therefore, force equal to F equal to alpha cross sectional area into pressure. Now work done is defined as force into displacement. That means work done, therefore work done equal to force into displacement. Force means F into displacement dx. It becomes force F equal to alpha p into dx. Now alpha into dx is a change in volume. That means alpha into dx, that change in volume, that means P into dV. This is the expression of work done. This is dV. That means that during this compression the volume of the system is decreasing. That means a dV should be negative in case of compression, and by convention we assume work done by the system is positive and work done on the system is negative. I repeat again, if I apply a force in this particular example, then the volume of the gaseous system should be decreased. So dV is a negative quantity. That means if I work on the system, due to decreasing value of dV, this work done will be negative. That's why we assume the work done on the system is a negative quantity and work done by the system is positive quantity. For compression, during compression volume of the system decreasing. So delta V alpha dx equal to minus dV, and hence dw equal to minus pdv. Okay, now graphical representation of work done. Graphical representation. Graphical representation. Graphical representation of work done. Representation. Graphical representation of work done. Graphical representation of work done. Suppose we take a PV diagram. This is V, this is P, PV diagram, and this is the initial state to final state. This is initial state I, and this is final state F. This is the initial state to final state. Then this PV diagram of a gaseous system with the work done is equal to this shaded area. That means the work done from initial state to final state becomes this shaded area. That means here we write as work done equal to Vi to Vf P dV, P into dV, and here we see that the volume increases. That means here we assume the work done by the system. That means this graph, suppose this is figure A. This is figure A. Then this PV diagram of a gas, the work done represented by the area of under the curve, by the shaded area of the curve, shaded area under the curve, and this is equal to P dV. Here dV is positive. Therefore we say that work done by the system. We say that work is done by the system. Work is done by the system. By the system. Similarly, in figure, suppose I assume this PV diagram. This is P, this is V, and this is initial, this is final state, and this is initial state. Final state to initial state. Here is the this is the initial state, this is the final state, and initial to final state direction is I to F. Now I consider from final state to initial state. Then the shaded area by the curve under the curve is this area. Therefore the work done particular from final state to initial state, it represents by Vi to Vf, Vi to Vf, here PdV, PdV. But here volume is here volume here volume decreasing, that means that is dV is negative. So we say that work is done not by the system, work is done by the system. Work done, this is work done by the system, this is work done by the system, this is work done by the system, and here work is done on the system. Here work is done on the system, this is work done on the system, and the work done is represented by the shaded area under the curve. This is negative, this is negative. Now if I consider this figure, this is figure B, this is figure B, and now figure C, this is initial step to final step here, and final step to initial step, initial to final, and here final to initial state. This is initial and final to again initial, final to initial. The area under the curve is represents the work done from I to F and F to I. Here is also work done is here PdV. So I can say that from this figure A, figure B, and figure C, figure A, figure B, and figure C, the work done is path dependent. The work done is path dependent. Now we take an example. Hydrostatic work depends on the path. Hydrostatic work depend on the path. Hydrostatic work depend on the path. Depends on the path. Now I take an initial equilibrium state I. Suppose this is PV diagram, this is P and this is V. PV diagram. Here I is initial state and here is final state. Initial state and final state. Suppose this is I2F, this is IAF, and this is just I take here, this is IBF, this is IBF, IBF, and another path, this is direct I2F. This is figure 1. This is figure 1. Figure 1. Here is dot 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 and dot dot dot. This is, suppose this is V0, this is 2V0, and here is P0. Suppose it is 2P0, P0 and 2P0. Suppose, okay. Now figure 1 shows the initial equilibrium state I and final equilibrium state F of a system. Initial equilibrium state is I, final equilibrium state is F of a system. There are many ways in which the system may expand from I to F. Here we consider three ways. One is I to F, A to F. Second is I to B to F, and direct along the diagonal from I to F, and direct from I to F along the diagonal. We consider three ways: IAF, IBF, and direct I to F along the diagonal. Now my aim is to find the work done, obtain the work done when the system is in initial state I and when the system is in initial state final state F, the work done in different path along the IAF, along IBF, and along IF. If from initial state to final state the work done in three different ways are different value, then we can say that the work done is path dependent. Now I calculate the work done in different path. Case 1. I to A pressure is constant. From I to A pressure constant. Pressure constant. Pressure is constant. Pressure constant. I to A pressure constant, and from A to F volume constant, and from A to F volume constant. Therefore the work done is equal to 2P0 into 2V0 minus V0. That means the area under this curve IAF, this is the area under, this is the area along the path IAF. That means the area represents the work done when we calculate the work done along IAF. So therefore it becomes 2P0 V0, 2P0 V0. This is equation 1. 2P0 times V0. Now case 2. Case 2. Case 2, along I to B volume is constant, and along B to F pressure is constant. Therefore work done along IBF, work done is represented by the area here, by the area this, by the area, this is the area when we calculate the work done along IBF. This is equal to P0 into 2V0 minus V0. That means P0 V0. This is equation 2. Now case 3. Case 3 along the path, I to F. The work done equal to, represent by the area under the curve IF. That means area, this area, that means this is the area, under the curve IF. Therefore this work done becomes P0 V0 plus half P0 V0. That means 3 half P0 V0. This is equation 3. Therefore we see that from equation 1, equation 2 and equation 3, work done depends not only on the initial and final state but also on the path or intermediate state. That means work done depends on path. This is very important conclusion, that work done depends on path. Now few example. The equation of state of an ideal gas is PV equal to nRT. Example, few example, some example. Some examples. First one, the equation of state of an ideal gas, problem 1, equal to PV equal to nRT. This is given, PV equal to nRT, where n and r are constant, n and r constant. Then find the volume expansivity beta. One is find so that volume expansivity beta equal to 1 by T. Beta is volume expansivity. And second one, so that isothermal compressibility Kt equal to 1 by P. So first of all, I have to know what is volume expansivity and what is isothermal compressibility. I already told in my previous lecture the definition of volume expansivity and isothermal compressibility. Beta and Kt. Beta equal to 1 by V del V del T at constant P, and isothermal compressibility Kt equal to minus 1 by V del P at constant T. Right? Now answer 1. First one, since beta equal to 1 by V del T at constant P, then from equation 1 we write, since PV equal to nRT, then we write 1 by V, and from here V by T. This is this del V del T at constant P. Using this relation, del V del T at constant P equal to, using this relation we get V by T. That means this is the value of 1 by T. At the same way, B equal to Kt equal to minus 1 by V del P at constant T equal to minus 1 by V del P at constant T. From this equation we write here minus V by P equal to 1 by P. So this is proved. del V del P equal to minus V by P, or minus 1 by V del P at constant T equal to 1 by P. Now another example. Work done for van der Waals gas. 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 Van der Waals gas. That means for real gas. The equation of state for van der Waals gas for 1 mole of van der Waals gas equal to RT. Here 1 mole of gas, this is PV equal to RT. Okay, or P equal to RT by V minus B minus A by V square. Therefore, for van der Waals gas, work done equal to VI integration VI to VF PdV equal to VI to VF. P means RT by V minus B, minus A by V square into dV. Therefore, we write work done for van der Waals gas. This is RT ln ln means log base E, VF minus B divided by VI minus B plus A times 1 by VF minus 1 by VI. This is the work done for van der Waals gas. Now another example. So that for van der Waals, for van der Waals gas, the equation of the adiabatic curve van der Waals gas, the equation of the adiabatic curve in terms of the variables T and V is given by R is given by T times V minus B whole to the power R by CV equal to constant, where it is given that dq, it is given dq equal to CV dt plus RT by V minus B dV, and del u del V at constant t equal to T del P del T del P del T V minus P. This is given. So I have to show this relation P T times V minus B whole to the power R by CV equal to constant. We have dq equal to CV dt plus RT by V minus B dV, right? Then in adiabatic case dq equal to 0. In adiabatic case dq equal to 0. Therefore CV dt equal to minus RT by V minus B into dV, or dt by t equal to minus R by CV minus R by CV times dV divided by V minus B, dV divided by V minus B. Now integrate this equation. We get, integrating this equation, we get ln t integrating ln t equal to minus R by CV ln V minus B plus ln C, where C is a constant. C is integrating constant. C is a constant. Or ln t equal to plus ln V minus B whole to the power R by CV equal to ln C, right? Or ln t into V minus B whole to the power R by CV equal to C, ln C. Or therefore thus t V minus B R by CV sum constant is equal to constant, because C is a constant. This is the expression proved. Okay.